Well, hello. I thought I was going to try another exercise just for the fun of it to see if I could create a model to predict the sun's position in the sky. Now, I already know personally what the outcome is, but just in case, if anybody is mathematically inclined and want to use this as an exercise, they can go over the equations and the formulas that I have to see if I've made any mistakes. But in short, according to the flat Earth model, the sun rotates above the Earth at a fixed distance, and one revolution around the Earth equals 24 hours. And here's a few images. So the way that I approached this was I went and I found an image, and I don't think I can find one any more authoritative than the Flat Earth Society globe map. And to simplify things, so this is 0 degrees longitude. If I were to put this on a Cartesian system, then I would need to rotate this counterclockwise so that this comes over here. That way there, any longitude in a negative direction would be calculated as an angle in this direction, and any longitude greater than 0 would be applied in this direction. The latitude would be the radius from the center of the map. 90 would be halfway, 180 would be the full distance. So I use that principle to convert the values to a Cartesian coordinate system, where the center of the map that you see here, that we associate as the North Pole, would be at 0 degrees on the 0 on the X and 0 on the Y. So the first thing I needed to do was to calculate the size. I found two tools. This one, I used 0 degrees north, 0 degrees west to 30 degrees north, 0 degrees west. And it gave me 3,320 kilometers distance. And if we multiply that by 3, it's 9960 point something. So it's just under 10,000 kilometers. And it's pretty close to what Google Maps gives from this coordinate to the North Pole. I took this number and I put it in a spreadsheet I created here. So then I took this, and because this is 30 degrees, the distance for 30 degrees on a flat Earth, you would take this number and essentially multiply it by 6. The sun's height is based on the distance between 45 degrees to the equator and the height of the sun to create a 45-degree angle. So because tangent of 45 is 1, we're able to use 45 degrees and to estimate the height of the sun, which is this. And this is going to be a quarter of the Earth's radius. So a quarter of the Earth's radius, or half of the distance from the equator to the center. This is where you would plug in your geocoordinates. This is the day that you want to look at the sun's position. This is the time zone for your local position. These calculate the sun's declination for that particular day. I'm not exactly sure what the proper definition is. I think the declination is the angle from the ecliptic and stuff like that. So, but it's based on, it changes from one extreme to the other, and this is the value for this particular day. This would be where the sun is on the equator at the 0 meridian on the equinox. These would be the observer's position on a Cartesian coordinate system. Local time is incremented 10 minutes. GMT time is offset from local time so that this represents the hours from GMT. And keep in mind that if GMT is always here, then we can calculate where the sun should be based on 24 hours. So hours divided by 24 multiplied by 360 will give us up to a full revolution, and then we just adjust for where we want the 0 degree angle. So that's why we have GMT time. Then the sun position is based on the observer's longitude, latitude, sun's declination, and GMT time. This column is the distance in the x direction between the sun and the observer. This column is the distance of the sun in the y direction to the observer. This represents the hypotenuse of these two. The azimuth is the angle between the observer and the sun, rotated so that an azimuth of 0 is always pointing back towards the center of the map. The altitude is the distance of the observer to the sun divided into the sun's height. And in the case where the distance between the observer and the sun is exactly 0, in other words, if the sun is directly overhead, then the altitude will be 90 degrees. So those are the formulas that I have to calculate the sun's position for 24 hours. I've used this tool a number of times, and this tool is accurate. If I say, where is the sun for my coordinate? So according to this tool, if I go and pick, let's say 450, on a flat Earth, the altitude should be 26 degrees and the azimuth should be 33. But according to this, the altitude is 0.77 degrees and the azimuth is 39. If I pick local solar noon, or they're very close to it, 2 p.m. Then I should have an altitude of 39.5 and an azimuth of 180. Now the azimuth is relatively correct and the altitude is not that far off. But you can see that the azimuth and the altitude really start going off the rails later in the day. So if I go and pick 11:20 p.m., I've got 26 and 328, and I should have 0.62 and 320. The closer you are to the center of the Earth, or in other words, the closer you are to the North Pole, it seems the more accurate this model is. 5:30 in the morning, 3181, 1479. The azimuth is correct in this case, the altitude is not. Let's go over here. 420, 31,245, 17,244. Let's go over here. 1040, 30 and 340, 10 and 339. So the azimuth seems very accurate at the North Pole, but the altitude is not. Let's try going in the other direction. Here. 650, 23.4, 44.5. 1074, 12 p.m., 71 and 0. Here we have 74 and an azimuth of 4. 6 p.m., 21 and 320. 1.8 and 285. A little bit further south. Let's try a latitude of minus 45. 720 for minus 45. 19 and 32. 1.7, 66. Local solar noon. 36, 0. 29 and 1. 450. 18.6 and 327. 2 and 294. So that's what I've come up with. I've come up with a spreadsheet that attempts to model the sun's movement in the sky and how we could observe it. And it just doesn't work as far as I can tell. So go ahead and take a look. Let me know if you come up with a better model. Otherwise, I would say that this is another proof that the Earth is not flat.